Most habitability models assume life is resilient. Rad Twin Xp challenges that by simulating a failure state biological twin, an XP-like cell under stellar UV stress. XP, or xeroderma pigmentosum, is a genetic disorder in which cells cannot properly repair UV-induced DNA lesions called CPDs. Current models prioritize planetary physics over molecular resilience, leaving us biologically blind to the point where DNA repair is overwhelmed. Rad Twin Xp solves this by predicting when UV stress pushes the system from stable recovery into persistent damage. Our solution is an interactive digital twin that connects stellar UV conditions, CPD damage kinetics, and a live biological response dashboard.
In synthetic M1 mode, we explore a generalized M-dwarf environment by changing stellar activity, stellar radius, orbital distance, and exposure duration. These inputs are mapped into an effective UV dose using interpolated stellar spectra and scaled radiation conditions, which then drive CPD formation in the cell. At the core, we use a literature-calibrated first-order damage and repair kinetic model to simulate how CPD accumulates and clears over time, using astrophysical input from hazmat spectra and biological calibration from published UV damage and XP repair studies.
The graph shows the key biological contrast. The healthy cell repairs and recovers, while the XP-like cell retains CPD damage much longer. After UV exposure stops, the system enters a repair-driven exponential decay phase, but with a much longer effective half-life in the repair-deficient case. On the right, we translate that molecular damage state into a simple synthetic stress visualization panel and an interpretable biological risk view.
We also built a TRAPPIST-1 preset mode to connect the model to a real exoplanetary system, where the same twin can be simulated across all 7 real planets. By selecting different planets, we change the orbital distance and UV stress, then instantly see how the biological response shifts.